Now, the spacecrafts were flying at about 55 kilometers over the surface, and they were able to return the best gravity map ever of any celestial body.
For decades, we were told the moon was a dead, silent rock. But inside its darkest craters, scientists have found something shocking: ice that could fuel rockets, and an invisible force that could cripple them. These frozen pits hold the key to building a base on the moon, but they may also be the most dangerous places any astronaut has ever stepped. Why? Because the shadows hide a deadly electric trap. Join us, the danger of the permanently shadowed regions. The most dangerous place on the moon is where the water is. That chilling warning, said to come from a NASA insider, sounds impossible at first. For decades, scientists dreamed of finding water beyond Earth, and when missions finally proved the moon had hidden reserves, it was celebrated as the key to colonization and the future of deep space travel. But what if those icy vaults are not a gift at all? What if the very places we thought would save us are actually silent death traps? And if we cannot reach them safely, does humanity's dream of building a home on the moon collapse before it even begins? These places are known as permanently shadowed regions, or PSRS, and they lie near the moon's north and south poles. Unlike the familiar equatorial plains that swing between scorching heat and deadly cold every 2 weeks, PSRS never see the sun at all. Because the moon barely tilts on its axis, the rims of certain polar craters block sunlight completely, leaving the floors in eternal darkness. Inside, the temperature falls below -200 degrees Celsius, colder than distant Pluto, colder than anything we could ever create on Earth. They are silent, airless, and blacker than the void of space itself. Yet beneath that endless darkness lie glittering deposits of ancient ice. Scientists once called them natural freezers, but today we know they are far more dangerous than anyone imagined. Here is the terrifying truth. The sun constantly blasts the moon with a stream of charged particles called the solar wind. These particles are mostly electrons and protons, but the electrons are much lighter and faster. When they slam into the moon, the electrons easily race into the shadowed craters, while the heavier ions lag behind. Over time, this imbalance leaves the crater floors loaded with excess negative charge. Meanwhile, the surrounding sunlit ground actually sheds electrons, making the electrical difference even sharper. The result is a hidden electrical trap. In plain terms, each crater becomes a massive, invisible battery. That is what makes these regions so terrifying. They are primed to spark. And when that spark comes, the consequences are devastating. Electronics can burn out in an instant, spacesuits can jolt with dangerous currents, and lunar dust, the most hated enemy of every Apollo astronaut, can turn into a deadly conductor. In these conditions, hundreds or even thousands of volts could build up silently, waiting for the slightest movement to release them in a blinding discharge. On Earth, static electricity is harmless because our atmosphere bleeds it away quickly. But on the moon, there is no air, no safe outlet. The only release is through sudden arcs of electricity, powerful enough to fry delicate machines or even threaten human lives. Now imagine a human mission. A team lands near the rim of a polar crater, preparing to confirm once and for all how much water lies hidden inside. One astronaut carefully steps into the darkness, their suit packed with the latest life support systems and communication gear. The suit is built to resist radiation and extreme cold, but it cannot change the fact that it is an isolated shell in a charged environment. Step by step, the charge builds. Then, without warning, an arc leaps across a connector at their life support pack. Alarms scream inside the helmet. The astronaut feels a jolt and their breathing spikes. For a split second, they do not know if their oxygen supply has failed. Their crewmates freeze in horror as the signal crackles in and out. It is the kind of nightmare no one has prepared for, and yet it could happen on the very missions meant to secure humanity's future. Even if sparks never fly, the moon has another hidden weapon: dust. Lunar regolith is razor-sharp, clinging to everything it touches, and it already caused chaos for Apollo astronauts. They complained that it coated their gloves, shredded their suits, and jammed their equipment. Now imagine that same dust electrified. It sticks tighter than ever, finds its way into seals and filters, smothers solar panels, and may even float above the surface in eerie clouds. If dust this sharp and toxic ever leaked into a habitat, it could scar lungs the way fine glass shards would on Earth. If it clogs cooling systems, entire machines could overheat and fail. On the moon, every single grain of dust is dangerous, and with electrical charge, it becomes a nightmare. So, the moon's poles may hold the water that humanity needs to survive in space, but they are not safe havens. They are hostile, unstable traps where darkness hides new discoveries and great risks. And if these craters are so dangerous, how did the water get there in the first place? That mystery changes everything. The truth about lunar water. For most of the 20th century, scientists believed the moon was bone dry. Apollo astronauts brought back rocks in the late 1960s and early 1970s, and when those samples were carefully examined, they appeared completely devoid of water. The conclusion seemed obvious at the time. With the moon's lack of atmosphere, no magnetic shield, and extreme surface temperatures. But a single assumption can collapse quickly in science, and the discovery of lunar water became one of the most dramatic reversals in space exploration. Hints began to emerge in the 1990s, when orbiters carrying radar instruments detected strange signals coming from the polar regions. Radar is sensitive to hydrogen, and some of these reflections suggested that the permanently shadowed craters near the poles might be hiding ice. At first, these results were controversial. Hydrogen can come from many sources, and radar echoes can be tricky to interpret. Was this truly frozen water, or something else entirely? Over the years, more missions joined the search. NASA's Lunar Prospector mapped hydrogen concentrations at both poles in 1998, giving researchers a clearer picture of polar cold traps where ice might survive. Then came the big breakthrough in 2009, when NASA deliberately crashed the LCROSS spacecraft into a crater near the South Pole. Instruments riding behind the impactor detected a towering plume of material, and inside it they found unmistakable signatures of water ice. In simple terms, scientists had thrown a probe into the darkness, and the moon spat out ice in return. Around the same time, India's Chandrayaan-1 orbiter used infrared spectrometers to detect water and hydroxyl molecules across the surface, even in regions exposed to sunlight. These missions shattered the old myth and forced everyone to rethink the moon's history. Sample returns confirmed the story. China's Chang'e 5 mission brought back lunar soil in 2020 that contained measurable water content, though at levels far lower than on Earth. These samples, combined with reanalysis of Apollo rocks using modern equipment, revealed tiny glass beads and mineral grains carrying traces of water or hydroxyl locked inside. Such findings proved that the moon was not just passively holding ancient ice in deep craters. It was an active world where water could form, move, and disappear. It was a revelation that forced scientists to ask a deeper question. If orbital sensors detect hydrogen, how do we know whether it represents actual water ice, hydroxyl, or just stray hydrogen atoms bound to minerals? Remote sensing can tell us there is hydrogen, but it cannot always reveal its exact chemical state. The surprises did not stop there. Instruments began to find signs of water even in areas exposed to direct sunlight, where temperatures soar to well above 100 degrees Celsius during lunar noon. How could water survive under such conditions? The answer lies in chemistry and timing. Protons from the solar wind constantly bombard the moon's surface. And when these positively charged particles strike oxygen atoms in lunar minerals, they can form hydroxyl groups. Some of these hydroxyl molecules combine further to create water. When the sun rises and heats the surface, these fragile molecules can hop across grains of dust, migrate to cooler areas, or even escape into space, only for the cycle to begin again when the sun sets. This means that a thin, transient layer of water can form and vanish on a daily cycle, a dynamic process that no one expected on a supposedly dead world. It raises a haunting question. If water can appear out of nothing more than solar particles and rock, how much more might be waiting in places we have not yet explored? Why does this matter so much for the future of space exploration? Because water is not just a scientific curiosity, it is a practical resource that can transform human missions. If astronauts can harvest ice on the moon, they can melt it for drinking water, split it into oxygen for breathing, and separate the hydrogen to make rocket fuel. This strategy, called In Situ Resource Utilization, or ISRU, could cut the cost of deep space missions dramatically. Launching water from Earth is extremely expensive because every kilogram adds to the rocket's mass, but if water can be mined and processed on the moon, it becomes a natural refueling station for journeys to Mars and beyond. Instead of carrying all the propellant from Earth, spacecraft could top up their tanks in lunar orbit or on the surface itself, opening the door to longer and more ambitious missions. But nothing on the moon is easy. Most of the ice detected so far is not lying on the surface like a frozen lake. It is mixed with lunar regolith, the dry, powdery soil that covers the moon, often buried beneath layers of rock and dust. Extracting this water will require energy to heat the soil, systems to trap the vapor, and equipment that can operate in extreme cold. Every kilogram of ice will demand careful planning, powerful technology, and a lot of patience. What seems like a limitless supply is in reality a collection of hard-won molecules locked in one of the most hostile environments in the solar system. This brings the story full circle. The very regions richest in ice are the ones hidden inside permanently shadowed craters, where temperatures plunge lower than anywhere else on the moon, and sunlight never reaches the ground. These cold traps hold the key to our survival beyond Earth, but they also present the greatest hazards, from electrical charges to deadly dust. Can we survive the moon's hidden charge? When we talk about the most dangerous places on the moon, it is not enough to simply say they are electrically charged. The real question is why they charge up in the first place, and how that charge can build to levels high enough to threaten astronauts and machines. The explanation begins with the solar wind, a steady stream of particles released by the sun that sweeps across the entire solar system. This wind carries both electrons, which are light and incredibly fast, and ions, which are heavier and slower. When these particles slam into the lunar surface, the electrons arrive first, and in far greater numbers. Because permanently shadowed craters never see sunlight, they cannot balance this constant flood of negative charge with photoemission, the process where sunlight kicks electrons back into space. Instead, electrons simply pile up in the darkness. The shape of these craters makes the problem worse. Their steep rims block out sunlight from every angle, so the shadows act like funnels, collecting and holding charge in places where nothing can bleed it away. Each shadowed basin turns into an invisible battery, storing energy silently until something gives it a path to discharge. This is not a theory waiting for proof. Laboratory experiments and computer simulations have recreated the conditions inside these dark craters and shown that charge separation is both real and persistent. When researchers simulated the solar wind striking rough surfaces, the imbalance between fast electrons and slower ions appeared almost immediately. Over time, voltages built up to levels measured in the hundreds or even thousands of volts, enough to spark across metal gaps and destroy electronics. triboelectric effects add another layer of danger. This word simply means frictional charging, like when you rub a balloon on your hair and it sticks. On the Moon, dust grains constantly rub against each other as they are disturbed by footsteps, wheels, or drills. In the vacuum of space, there is no atmosphere or moisture to neutralize those charges. Each grain becomes a tiny capacitor, and together they create clouds of clingy, abrasive particles that refuse to let go once they touch a surface. The combination of solar wind charging and triboelectric charging turns these shadowed regions into volatile traps of hidden electricity. The consequences for hardware are straightforward but alarming. Electronics exposed to sudden discharges can experience shorts, wiping memory or frying sensors without warning. Motors designed to drill into the soil may suddenly stall if charged dust clogs their moving parts, adding unexpected resistance until they seize. Communication systems could misread signals if static builds up along transmission lines. Even more dangerous, spacesuits can act like capacitors, collecting charge across their surface until one sudden spark jumps to a connector or joint. Every hinge, every filter, every moving part risks faster wear and sudden failure if abrasive, electrically active dust embeds itself where it should not. The Moon is already a harsh place for machines, but electrification raises the stakes to a level that makes even experienced engineers uneasy. Imagine one realistic scenario. A rover crew deploys a drill near the rim of a polar crater, targeting regolith expected to hold traces of ice. The auger begins cutting into the soil, but charged dust immediately clings to the metal flutes instead of being cleared away. With every rotation, the material sticks tighter until the motor overheats from the strain. Operators attempt to retract the drill, but static discharges arc into the control electronics, tripping protective circuits and shutting the system down. In the end, the instrument is jammed, the mission loses valuable time, and the chances of recovery are slim. Nothing explodes, yet the loss of one critical tool means an entire expedition can fall behind schedule and budget, and in spaceflight, those costs are measured in millions of dollars and months of delay. Engineers are racing to counter these threats. Suit designs now include conductive threads woven into the outer layers to help spread and drain charge before it can build to dangerous levels. Boots may contain grounding strips that slowly discharge energy with every step, while connectors are being redesigned to stay bonded even when sparks attempt to leap across gaps. Astronauts may need to follow strict discharge protocols, touching designated grounding points before approaching sensitive equipment to avoid hidden shocks. Robots and tools are also being hardened. Conductive coatings allow charge to drain harmlessly instead of building on housings. Sample systems may be enclosed in sealed containers to keep dust out entirely. Some mission plans call for deploying grounding masts before astronauts enter a crater, giving electrons a controlled path to escape, or using tethered return lines that constantly draw off charge during operations. None of these fixes are elegant, but they may be essential if exploration is to continue safely. Dust remains the most stubborn problem. Several technologies are in testing, each with trade-offs. Electromagnetic shields attempt to repel charged particles with active fields, but they consume large amounts of energy. Electrostatic dust wipers sweep dust away using voltage differences, though they must be carefully tuned to avoid damaging surfaces. Cryogenic capture freezes dust onto cold plates, which requires bulky cooling systems. Inertial separators shake particles loose using motion and airflow, but moving air is hard to generate in a vacuum. Each method works under certain conditions, yet none provides a single guaranteed solution. Engineers must weigh energy costs, weight limits, and reliability before choosing any system. Navigation and site selection add another strategic layer. Missions may choose to avoid the deepest shadowed regions altogether, targeting sunlit areas with trace water instead of diving into the coldest traps. Sample return missions could stage from the fringes of craters, where sunlight provides power and reduces charging risk, and only send small robotic probes into the darkest zones. This approach reduces danger but limits access to the richest reserves, setting up a constant trade-off between safety and reward. These technical realities are already shaping mission planning. Future lunar spacewalks will likely be slower, with astronauts required to follow strict charge bleeding protocols at regular intervals. Remote teleoperations, where human operators on the surface or in orbit control robotic systems inside craters, may become the preferred first step before anyone sets foot in the deepest shadows. Incremental missions will likely test new equipment piece by piece before full-scale mining begins. Each safeguard adds cost and time, and political leaders who fund these programs will have to accept that large-scale extraction of lunar ice may be delayed if mitigation proves too expensive or unreliable. So how dangerous is this problem really? It is serious, but not impossible to manage. Electrical charging in lunar shadowed regions will not make exploration impossible, but it will make it slower, costlier, and more complex. The technology exists to control it, yet every added safeguard means more weight on rockets, more power consumption on the surface, and more dollars spent back on Earth. As one insider put it in a candid moment, engineers are cautiously optimistic, but fully aware that the moon does not give up its resources easily. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.